lesson 2.4, day 2, we had talked about example 5 at the top of the page, right? We were talking about differentiability, whether it was differentiable. We had to check those problem areas. And so, continuing down here, although we're looking more now at the definition of continuity, or back at continuity, but piecewise functions, always challenging. Not only do the limits of the slopes need to be approaching the same value on either side of a given x value, but the function must be connected and smooth in order for the function to be differentiable. So again, it has to be continuous, which a piecewise function you don't know until you do some checking, right? But then we have to have connected smooth graph for it to be differentiable as well. So example 6, find the values of the constant a where the function is continuous over all reals. We've done this before. What do we do? Set them equal to each other, essentially. I mean, the official terminology would be we're setting the limits equal to each other, yes? That's the official. Officially, we want the limit as x approaches 3 from the left, which is going to be, which one's the left? Ax squared minus x, to equal the limit as x approaches 3 from the right of 2a to equal each other. But the short of it is, yes, set them equal to each other. Okay. In a free response problem, you're going to want to use the limit notation to start yourself off. Now, I know, like, when you look at answer key and stuff on this upcoming assignment, and, like, I don't know, see, I can't tell by looking at mine if she had limits here or not, but that is the idea. Okay, so if we're doing the limit as x approaches 3, we're going to put 3 in, putting 3 in for x, right? So a times 3 squared minus 3 over here is just 2a because there's no x value, right? So find a. (9a minus 3 equals 2a. I'm going to subtract 2a and say 7a. I'm going to add 3. I'm going to come up with a is 3/7. So officially, all it asks us to do is find the value of a where the function is continuous, yes? Which that would be the function that would make it continuous. Now, since we're talking about differentiability, okay, I want to talk briefly about, okay, how can we show, or maybe shall I say justify, that this is differentiable? And then we don't want to look at the limits so much as we do of the limits of the slopes, if you will. I'm looking at what I did here to see if this makes sense. Oh, okay. Sorry, I can't figure out what I did. This is actually, never mind, I was misreading my own writing there. This is actually to just justify the continuous. So basically to kind of show that that 3/7 does work. And so in other words, if we're going to show that that 3/7 does work, basically putting it in place of a. So if we look at, same thing, the limit as x approaches 3, but instead of ax squared minus x, what value are we using for a this time? We're doing 3/7 x squared minus x, and equal to the limit as x approaches 3 from the right, and that's going to be 2 times a, which is going to be 2 times 3/7. Sorry, I was misreading my own handwriting there. And so if we're checking that, this is just to kind of justify and prove it, so to speak, that both sides do end up equal. So again, you're plugging the 3 in. 3/7 times 3 squared minus 3, and then equal to the 2 times 3/7. 3 squared is 9. 9 times 3 is going to make this 27/7 minus 3 equaling to 2 times 3/7 is 6/7. Although, how do we subtract 3 from 27/7? Yeah. We're going to think 27/7 minus 21/7. And guess what? 27/7 minus 21/7 is 6/7. And so that's your justification, just showing that it did work out. So again, reminding you, how do we check and see if something is continuous? Okay, or where do we find, in this case, the value where it's continuous? You have some of those problems in homework. Because when I started doing the homework, I was like, wow, this is stuff we've done. Okay, we've done this type of problem before, haven't we? Okay. Okay. Example 7. Show, notice it says, algebraically, using the alternate form of the derivative, why g of x is not differentiable at x equals 1. Excuse me. So, in order to not be we're trying to show differentiability, or in this case, lack thereof, what do we need to think about first?
Like, is the slopes equal to each other?
Right? Are the slopes equal to each other? And so, if the slopes are equal to each other, then we're talking definition of derivative, yes? And so, as we talk definition of derivative, specifically said to use the alternate form. Excuse me. Set this up weird in my notes. Okay, so if we look, first of all, at the limit as x approaches, you want to do left or right first? 1 from the left of f prime of x. And so, remember it's saying to use alternate form. Excuse me. Limit as x approaches 1 from the left. Do you remember alternate form? It's f of x, which is the left one? It's x squared, isn't it? So f of x, which is x squared minus f of 1, which is going to be 1 squared, over x minus 1. Are you guys okay with that? Sorry, my brain is being a little foggy for the moment. Okay. We know x squared minus 1 is just x squared minus 1, right? What do you know about that numerator? It factors, doesn't it? So that factors into x plus 1, x minus 1, over the x minus 1 that's there. X minus 1's cancel, and we end up with the limit as x approaches 1 from the left of x plus 1. When we plug in 1 there, we're going to get 1 plus 1, which is 2. Okay, that was the left. Now let's check the right. Limit as x approaches 1 from the right of the derivative. So the limit as x approaches 1 from the right. This time, we're using the bottom one, yes? So now we're using the function, since x approaches 1 from the right, we're using x as our function, minus f of 1. Well, when you put in 1 for x, it's going to be 1, so x minus 1, over x minus your a value, so x minus 1. What happens there? It cancels, right? And when those cancel, what you're basically saying is the limit as x approaches 1 from the right of 1, which is just going to be 1. Okay. What did we just discover? They're not equal, are they? Okay, as we look at this, 2 is not equal to 1, so these limits were not equal to each other. The directions were to show algebraically why it is not differentiable. Have we done that? Yeah, we did that by looking at basically the derivative of the left, derivative of the right. We found different derivatives. Now, graphically, can you graph this with me? I just realized I called this F all along. It was technically G. Am I the only one that's guilty of not grabbing the right thing there?
The graph is also without the lines.
It does say, oh, okay, see, there's my defense. Okay, so when we graph this, you guys know how to graph this piecewise? To the left of 1, my function is x squared. So what do you know about x squared?
Yeah.
It's a parabola centered at 0, 0, and where are the first sets of dots?
1.
Right one up one and left one up one, yes? Now, to the left, we could also, if we wanted to, go up to like, say, 2, 4, like that would be the next dot. On the right, do I need to go up to 2, 4? No, because 1 is my dividing piece. So this is saying it's a parabola over here, right? And this side, it's a parabola that ends right there. What about when x is bigger than 1? What is this? When x is bigger than 1, it's a line, y equals x. What's the line y equals x? Normally we say it goes through the x-intercept of 0, but then it has a point, slope of 1, so rise 1, run 1, which puts us at 1, 1, 2, 2, 3, 3, 4, 4. So now my graph continues this way. I don't like how my graph turned out, to be honest. It doesn't show what I need it to show. But in that, okay, what's the idea? We found that this is not differentiable, yes? So my graph doesn't really look it. But what is probably happening at 1? What? It's not that it's removable. It's not that there's a hole, because it does say it's equal to 1. But if I drew this differently, there's probably like a hard point, cusp. My graph just doesn't really look like it, does it? My graph just kind of looks like it flows. But that's where you realize when you combine two graphs, it might be okay. It might form a hard point. Sharp point, what did I write in here? I have it written down as a cusp. I really need to look into difference between a cusp and like a hard point or sharp point, because I feel like they're the same, really. But, so, graphically, there is a cusp at x equals 1. So I know it asks us for algebraically, but I also, trying to make all the connections here. Okay. Ready for the next part? I must say, I'm struggling with this next part a little bit in that we haven't learned how to do derivatives the quick way yet. But yeah, I'm going to show you how you can find the derivative at a certain point on your calculator. Kind of backwards in my mind. I never introduced the calculator until much later in Saxon, but that's all right. I'm going to go with it. So none of us have the Inspire, so you guys can ignore this part. But you guys all use the TI-84 Plus. And I have to figure out what the fourth is. There's 4 things that when you go that you're allowed to use your calculator for. And like you really don't have to show the work. On the calculator section, one of the things is your calculator will not find a derivative. Like it won't find a derivative of a function. But it will evaluate, if you know the function and you want to know what the derivative is, evaluate at a certain point, it will do that for you. It won't tell you, okay, the derivative of x squared is 2x. But it would tell you the derivative of x squared at 3 is 6. Okay? So there is some stuff your calculator can do. That's one of the things that you're allowed to do on the AP test. Derivatives, integrals, you're allowed to use a graph. I don't know, there's something else. But, so, okay. On the AP exam, you'll need to be able to find a numeric derivative of a function at a given point. And that's what I'm talking about, at a given point. In deriv. So where you guys want to go is you want to use your math menu. Number 8. Okay. And you can practice with this one right here. Math 8, what do you go down to, or math? And is it number 8? Is that what it is? And it brings up a little fill in the blank thing, yes?
Yeah.
Okay. So, the blanks you're filling in. You have to fill in, when it's d over d blank, you're filling in with what variable are you integrating with respect to. Default answer, x. Okay, so you're filling in x. You fill in whatever your function is here. So this is whatever your function is. You fill that in there. And then you have to fill in your x value. So, it's asking us here to use the calculator to find the derivative of x squared minus 5x plus 6 at x equals negative 3. Express your answer using proper notation. So, did you get it? d dx of x squared minus 5x plus 6 evaluated at x equals negative 3. That's what your calculator said. What did you guys get for the answer? The negative 11 that is displayed on the notes?
Yeah.
Okay. If you didn't, let's figure out where things are going wrong. Now, is this one where radians versus degrees could affect it? Only if you're using a trig function. Then it would affect it. But that doesn't use a trig function. Now, if we did this if I show you, and I know it doesn't make any sense yet, I think it's coming up pretty soon here. But if I show you x squared minus 5x plus 6, the derivative of x squared minus 5x plus 6 is 2x minus 5. And so what we just did is we took that and plugged negative 3 in. So 2 times negative 3 minus 5. Well, guess what? That's negative 6 minus 5, which is negative 11. So, you know, that'll come up eventually where that's an easy derivative to find, and you'll be able to plug it in and get the answer. The calculator can do that for you. You just have to know the function and the value you're evaluating at. Okay? That's a very basic function. Your calculator is always going to do that one right. Okay, your calculator's not going to mess that one up. And in all honesty, the ones you have to do, your calculator's not going to usually mess them up. However, on the next page, it talks about using the calculator to find derivative of our first 3 functions in this lesson set. Explain any problems that you encounter. Now, I watched the video of this part, and she demonstrated also with the Inspire, which is a fancier calculator, pretty much. It's more of almost, I don't know if I want to say computer-based, or, I mean, all calculators are computer-based, but it's a little more closer to a mini computer, okay? And it was a little more accurate than some of these. Now, these things that we're looking at the problem zones pretty much, okay? So like when we look at A, okay? So this goes back, and you can go back and look at, where did we do this? Back at the very beginning there, example 1. we already found out that this is not differentiable at x equals 1, correct? Well, what happens when you put this in your calculator? So if you put in your calculator d dx of absolute value x minus 1 evaluated at x equals 1. Huh?
This is
It says 0?
Where's the absolute value sign?
I use the shortcut alpha F2. It's also in the math menu. Yeah, that's right there, EDS. Yeah, I use that one. It's also in the math menu, I don't know, somewhere. I don't remember where. Learning. Now, officially, what's happening? If you think about the graph, absolute value of x minus 1, which minus 1, remember, moves it right 1. Well, officially, there's a problem spot there, isn't there? Because that is a hard point. That is a sharp corner. And so right there, officially, you cannot take the derivative there. So all this to say, basically, kind of like if you recall from pre-calc, the graphing part would kind of fail at times and be hard to read it. Don't fall into the false sense of, oh, it gave me a derivative. It's differentiable there. The derivative exists there. Okay? So, I think on this one, I wrote down that the inspire gave plus or minus 1. Which makes a little bit more sense because the slope from the right is 1, the slope from the left is negative 1. So it makes a little bit more sense, but it still doesn't work there. Okay? I'm going to say actual, because I don't want you to walk away thinking it does there. Okay. Does not exist. Have you tried B yet? d dx of the cube root of x evaluated at x equals 0. Cube root I find in the alpha F2 or in the math menu. Right? I think it's in alpha F2 if I recall.
See, I just remember it's math 4.
Okay.
Even though it's a cube root, it's 4.
Okay. I don't know exactly where it's at. I just know it's, But it's one of those things. When did we last use some of these pieces, right? What's your calculator saying? 100. Okay. So we graph this one also. Remember the cube root? It's taking x cubed, which is kind of that vertical curve, and it's making it horizontal, right? So cube root of x looks something like that. And that's not perfect there, because I think I'm supposed to be probably a little more flat there. I think it's probably supposed to be a little bit more flat there. Because what happens? That makes it a vertical tangent, yes? Well, 100, the only thing I can figure out, 100 is very steep, isn't it? But in all reality, the derivative does not exist, right? Or maybe I should just say actual. Okay, and that's because there would be a vertical tangent there. This one, let's see, the Inspire actually did this one right. Okay, and C. Practice entering C. d dx of 1 over x plus 2 squared evaluated at x equals negative 2. At least you're getting the pros of using, putting it all in. Did you get an answer?
2.
0? Okay. Now, if you go back to the graph we did at the beginning, x plus 2, 1 over x plus 2 squared is, there's a vertical asymptote at -2. And my graph approaches that asymptote from both sides. If there's a vertical asymptote, can we have a slope of 0 at that point? No. Okay. So again, I'm going to say in all actuality, it does not exist. So now, in all honesty, how often does this happen with what the problems you're doing on your calculator? It doesn't. Okay. The side note down here is your calculator is programmed to find derivatives by using the symmetric difference quotient. This can cause errors. You must make the final decision based on proper analysis. And that's what I'm showing you here. Most of the time when you're asked to do a derivative on the calculator, though, you're just getting the information to speed up the problem. Okay? So it's not that you run into this a bunch. Okay. One last piece. Defending your answers. If you're given that y equals f of x is a differentiable function at x equals 3, explain why each statement below is true. Okay. Did you guys understand what they're asking there? I didn't for a brief moment. What's the given information? F of x is differentiable. If that's the information I'm told, and of course that is at x equals 3, how do I know f of 3 exists? What's my defense there? Okay, if it's differentiable, what does that tell me?
It's continuous.
It's continuous, right? Differentiability implies continuity. So if it's differentiable, it's continuous. Does that help me out here? If a graph is continuous, what does that mean happens at that point? It must exist, right? The limit from the left equals the limit from the right, and it equals the value of the point there. Okay, so my defense is that if f is differentiable, then f is continuous. And as soon as you say continuous, then by definition of continuity, we say f of 3 must exist. Basically, you have to get to continuous to say that point exists. And by saying it's differentiable, we do that. Along the same lines, the limit as x approaches 3 of f of x exists. Well, what do we know? Huh? Well, just go back to, we know it's differentiable. Go back to, that's the only given information we know. It's differentiable. But what does differentiable tell me? It's continuous. What do we know about continuity? If it's continuous, the limit exists, and that point exists, right? It's the limit from the left equals the limit from the right, but the limit exists. So again, since f is differentiable, it's continuous, and thus the limit must exist. So, can I shorthand this? Since f is diff, and it's also continuous, so I can say that the limit as x approaches 3 of f of x must exist. What about C? Do you recognize that? This is one of those things I want you to get in the habit of recognizing. What are they giving us there?
That's your alternate form.
Is that a definition of derivative? That is alternate form of definition of derivative. So must that exist? Yes, because at that point it is differentiable. So if it's differentiable at that point, that means we can take the derivative at that point. And so how do I want to put this? I'm going to say since differentiable, derivative must exist. And this is alternate, what do we say? Alternate definition of derivative, alternate form, alternate definition of derivative. Sorry, kind of, I don't know. Lots of writing here. I'm doing a lot of shorthanding. You can figure it out though, right? And I don't know if it helps you on this one or not, but basically this was the form at limit as x approaches a of f of x minus f of a over x minus a, right? That's the form. And that's what you need to be able to recognize, right? I told you that from the beginning. That's why I have to teach definition of derivative, because you have to be able to recognize that. Okay, what about D? What is that? Is that our normal limit definition of derivative? It is. So, you know, same things as above. This is our limit definition of derivative. This is the limit as h approaches 0 of, now normally we say f of x plus h minus f of x all over h. Except at this point the x value is 3 and it's already plugged in. Okay? I'm done, right? I am. Okay. Unusual day.
Yeah.
We're done early. Enjoy while you can, right?